Desalination is the key to unlocking 97% of the world's water, but the way we do it today isn't great. Desalination plants suck in billions of gallons of seawater and treat it with a load of chemicals, killing fish and larvae in the process. They burn an insane amount of energy to pressurize that water to 600 to 1000 psi, and then dump a toxic brine sludge back into the ocean, creating massive dead zones where nothing can survive. But what if I told you that we've been doing it wrong? One company says the solution isn't to build bigger factories on land, it's to sink them to the bottom of the ocean and use its crushing weight to desalinate water for free. Is this the holy grail of infinite fresh water, or is it an engineering nightmare waiting to implode? Let's figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Jackery. So what exactly is the idea here? The company I'm talking about is called OceanWell, and they're taking a completely different approach to desalination. They're building modular desalination pods that leverage the ocean's crushing hydrostatic pressure at depths of 400 to 600 meters or 1,300 to 2,000 feet. The pods use this pressure to push the salt water through a reverse osmosis or RO membrane and generate cool, clean, and fresh water without using a high-pressure pump. We'll get into the details of how they build, deploy, and maintain them here in a minute. But for now, I want to leave you with the amazing benefits this approach has compared to traditional desalination that make it a no-brainer solution to our water problems. As I said, they don't have to pressurize the input water because it's already pressurized by the ocean's weight. So you're saving on massive and expensive high-pressure pumps and the energy to run them. They only have to use pumps to pump water back up to the surface. These benefits alone slash around 40% of the energy used by a normal onshore RO plant, from 3 kilowatt-hours to 1.8 kilowatt-hours per cubic meter. They have an unlimited supply of seawater, so they don't need to extract every possible ounce of fresh water from it. This adds a ton of benefits in terms of the membrane specs and possible lifespan. They also don't need to pre-treat the water with harsh chemicals before driving it through the membranes. These two benefits also mean that the discarded brine is less concentrated and not as toxic as the ones that come from a normal RO plant. Furthermore, thanks to these sort of hoses here, the less concentrated brine is discarded away from the seafloor directly into the ocean currents that immediately mix and disperse the brine, diluting it and carrying it away in a part of the ocean that is already almost devoid of life. So the environmental impact of desalination in this case is minimal, almost negligible. But here's the thing that keeps bugging me. Today, roughly 69% of all desalination still comes from RO plants, which is weird because a technology that was invented in the 1950s is still the leader when it comes to desalination. When so much else has changed, why is that the case? The answer, as usual, comes down to the numbers, economics, and thermodynamics. Right now, RO is simply the most energy efficient, commercially viable option to have for large-scale production. Thermodynamic limits dictate that you need a minimum amount of energy to separate salt from water, and modern RO gets closer to that theoretical limit than most other methods. So why not just build RO plants everywhere and save the day? Because standard RO has a dark side. It's an engineering trade-off that is becoming dangerous. First, there's the waste. For every liter of fresh water we squeeze out, we produce about 1 to 1.5 liters of brine, a hyper-salty sludge often laced with chemicals like chlorine, copper, sulfuric acid, and polyethylene glycol used in the cleaning process to prevent scaling. One study found that globally, desalination plants produce 51.8 billion cubic meters of brine each year, enough to cover the entire state of Florida a foot deep. When we dump that brine back into the ocean, it sinks. It creates a toxic layer on the seafloor that chokes marine life and destroys ecosystems. Now, that doesn't sound to me like a very sustainable option for every part around the world. We need the reliability and efficiency of reverse osmosis, but without the massive energy penalty and the environmental destruction. And we just need to do it better. We've covered other ways of doing this, right? We could capture the brine, evaporate it, sell the salt and chlorine and lithium from it. We cover these kinds of innovations for this very reason. And for those reasons, deep sea desalination could be a game changer. This is truly a golden age of sustainable tech, with investments in everything from deep sea desalination to solar and batteries. And when it comes to tech that you can actually buy today, our sponsor Jackery has you covered. These are my 3 favorite things that I saw at the Jackery booth at CES. First, the new Jackery Solar Gazebo. This beautiful and metal gazebo houses 2,000 watts of solar panels on the roof with built-in lights, fans, louvered shutters, and retractable shades. Enjoy the outdoors in style. I love the look, and having gotten a quote recently for a backyard patio, I really think this is a great value. Combine this with the Jackery Explorer 5000, and you have outdoor power without trenching or expensive electrician visits. Second, and probably my favorite, is the Jackery Solar Mars bot that autonomously follows users, avoids shade, and tilts to track the sun all day long for maximum production up to 600 watts of power. Whether it's camping trips or festivals or even emergency response, this awesome bit of tech provides power wherever you need it. Finally, the Explorer 1500 Ultra, a true workhorse in portable power. Rugged, portable, and all-weather, you can take this thing anywhere. It's IP65 rated, dustproof, and waterproof, and Jackery always makes some of the lightest and smallest batteries in each category. Now, this is my go-to battery for things like powering my Starlink or my computers, lights, and camera gear, e-bikes, and all that sort of stuff on travel. They have a ton of new amazing releases. Learn more about Jackery's awesome new lineup using our links in the description for the best prices today. Huge thanks to Jackery and you. Now back to the show. To understand why this new tech is genius, we first have to put on our engineering hats and pay respects to the enemy, osmotic pressure. Imagine a tank divided by a membrane or a molecular filter that only lets water through. You put salt water on one side and fresh on the other. Nature hates imbalance, so it wants to equalize the concentrations on both sides. Since a membrane only lets water through, the only way to do that is for the fresh water to flow into the salty side to dilute it. A process called osmosis. That would be the natural outcome, but it's the opposite of what we want. The force that drives it is osmotic pressure, and it's actually really easy to calculate from the salinity and the temperature. When you put in ocean water's average salinity of 3.5% and do some unit conversions, you get an osmotic pressure of 28 to 30 bars, or around 410 to 440 psi. That means at pressures of around 440 psi, we're only stopping the osmotic pressure. The water just sits there. To actually reverse the osmotic process and produce water at a reasonable rate, we need to reach between 600 and 900 psi. Generating that kind of pressure requires massive, energy-hungry pumps. This is where 40 to 60% of the cost of desalinated water comes from. But what if we didn't have to build the pressure? What if we just went to where the pressure already exists? As a rule of thumb, for every 10 meters you go down, pressure increases by 1 atmosphere, about 14.7 psi. So to reach 600 to 900 psi, we need to go down roughly 400 to 600 meters. Down there, the weight of the ocean itself provides all the crushing force we need effectively for free. But if you're thinking about pressures here, you've probably spotted the flaw of this logic immediately. The problem isn't generating the pressure of 900 psi. The real problem is generating a pressure differential of 900 psi. If we take one of those pods down at 600 meters, the seawater outside the box is at 900 psi, but so is the inside. There's no pressure differential, so there's no reverse osmosis. Think about like a balloon. If you blow up a balloon, the pressure inside the balloon is a lot higher than the surrounding air. So if you let go of that balloon, that air is going to come rushing out. At some point, the air will stop moving. When? When the pressure outside and inside the balloon is identical. At that point, there is no transfer, there's no pressure differential. So how does OceanWell create that difference? Well, with a large 600 to 900 psi pump. Now think about that for a minute. You're going through all the trouble of putting the desalination plant 600 meters underwater to avoid using a pump to pump seawater at 900 psi on shore, just to put another pump 600 meters underwater so you can generate a negative pressure of the same 900 psi. That seemingly makes no sense. Like, what is the point then of doing this whole thing? By placing a pump on the freshwater side of the membrane, they pump the freshwater up to the surface. This lowers the pressure on the clean side of the membrane, creating the massive 900 psi differential we need. Nature pushes the seawater against the membrane, and the pump simply lifts the freshwater away. Now, if you're thinking, hold on, Ricky, we're still using a pump. What's the difference? You're right. The difference is mass. And in engineering, mass is money. In a standard RO plant on land, to get 1 liter of fresh water, you have to pressurize roughly 2 to 2.5 liters of seawater. You're spending 50 to 60% of the pump's energy on water that effectively becomes waste brine. In this deep sea system, the ocean pressurizes the feed water for free. And all you're doing is pumping the fresh water that you keep. You're moving less than half the mass. Mathematically, you've instantly slashed your primary energy requirement by more than 50%. It's elegant, efficient, and uses gravity to do the heavy lifting. Now, I know our viewers, and you're probably thinking, reverse osmosis plants have already solved this problem. We have energy recovery devices. And you're right. Modern plants use these incredible devices called isobaric pressure exchangers. They take the high pressure brine to basically spin a compressor and transfer over 95% of that energy directly to the incoming seawater. Because of them, we've dropped the energy cost of desalinated water massively over the last 20 years. It's like using waste heat from a process instead of just dumping it back to the environment. It's like so many other things that you can recover energy from. And it's cool, and we're already doing it today. Again, it's a little bit counterintuitive. It's what makes these episodes so much fun. But the difference is the volume trap. First, in a traditional land-based plant, even with a 96% efficient energy recovery device, you're still losing 4% of the energy in the brine. But you're also moving the entire volume of water and the brine through the intake pipes, pre-treatment screens, high-pressure pumps, and outtake pumps. You're managing the friction and flow of the entire ocean water stream. In the deep sea system, you only pump the fresh water up to the surface. The energy to move the feed water and brine is completely free. But there's more. The energy cost of a desalination plant isn't just the RO pump, it's the pre-treatment. Remember that toxic brine problem? That happens because the first 200 meters of surface water is alive. It gets sunlight, so it's full of algae, bacteria, and barnacle larvae that love to clog up filters. Before you even think about doing reverse osmosis, you have to pump that water through massive sand filters, dissolved air flotation tanks, and cartridge filters. All that machinery costs millions to build and run. But below 200 meters, we enter the aphotic zone, the midnight zone. There is no sunlight, no photosynthesis, no algae. The diversity of life drops dramatically as we go down. At 600 meters, it's mostly just cold, clear water. Because the water is so clean, the system doesn't need the harsh pre-treatment chemicals that land-based systems do. And for the amount of zooplankton we might have down there, the system uses a low-velocity intake. Think of it like a gentle vacuum cleaner versus a jet engine. The suction is so low that sea life isn't sucked in. They just swim past it. And any that do get sucked in are caught by a series of fine filters and later dislodged and released back into the water. But the coolest part is because they aren't paying for pressurizing the feed water, we can afford to be inefficient with the water itself. We can run the system at a very low recovery rate, say 10% or 15%, instead of 40 or 50% like we do onshore. This means the brine we release is 5 to 9 times less concentrated than normal onshore brine, and it mixes instantly with the ocean current. Finally, there's another small but contributing factor at play, which is buoyancy. Fresh water is less dense or lighter than seawater. The difference is very small, but it does make pumping it up 600 meters a little bit easier, acting as a natural buoyancy pump. One extra advantage is temperature. Water at 5 to 600 meters deep is freezing cold, near 4 degrees Celsius. OceanWell plans to use this cold water for district cooling to get even more value from the system. This turns out to be great, since most water-stressed coastal regions where the system would work also happen to be pretty hot places. So we have a system that uses half the energy, produces no chemical waste, doesn't harm marine life, and can cool our homes. This begs the question, if the physics work and the economics seem solid, why isn't this everywhere yet? And if you've been watching us for a while, you know in engineering, there are always trade-offs. We just spent 10 minutes talking about how this system saves energy, saves marine life, and uses gravity for free. So what is the trade-off here? Well, the trade-off in this case is in logistics. The first thing is maintenance. In a traditional land-based plant, if a valve gets stuck or a sensor fails, you call Bob. Bob drives his truck to the shed, walks over with a wrench, and fixes it in 20 minutes. It costs $50 and a couple of cups of coffee. At 600 meters deep, Bob needs a multi-million-dollar offshore support vessel, a specialized crane, and a remotely operated vehicle piloted by a team of experts. You can't just fix things. You have to design the entire system to be modular, swapping out the entire cassette or pod rather than repairing individual components. OceanWell's design relies on retrieving these pods to the surface for maintenance, but they're working on design cartridge systems that can be serviced by autonomous drones. We also have to talk about the environment. Saltwater is already the enemy of metal, but at 600 meters, we're dealing with high pressure, cold temperatures, and constant salinity. Corrosion is relentless. Every seal, every bolt, and every electrical connector has to be marine grade on steroids. If a seal fails on land, you get a puddle. If it fails at 600 meters, the ocean implodes your equipment. A few decades ago, this wouldn't have worked, but OceanWell is leveraging long-standing technology from the offshore oil and gas industry, which has a lot of experience working with pumps at the sea floor. In fact, most of the oil industry's systems are actually over-engineered for desalination, since you don't really need such strict leak prevention tolerances because a leak is just pure, clean drinking water, not oil. There is one more massive constraint that we have to talk about: bathymetry, or the shape of the ocean floor. For this to work, you have to hit that sweet spot of depth between 400 to 600 meters. But you also need to be close enough to the shore so that you aren't spending billions laying horizontal pipelines and umbilical cords to run the pump. This creates a serious case of the haves and have-nots. Take the US, for example. On the East Coast, like New York and Florida, the continental shelf creates a long, shallow slope. To reach 600 meters of depth, you might have to travel 100 miles offshore. At that distance, the cost of pumping water back to the coast destroys all energy savings due to friction, loss, and construction cost. It's a non-starter. But on the West Coast, like California, the shelf drops off like a cliff. You can hit deep water in just 3 to 5 miles offshore. This creates a Goldilocks zone where the depth is right and the distance is short. So OceanWell isn't a global silver bullet. It is a targeted surgical tool for specific locations. Places like California, Chile, and parts of Africa, where the mountain basically falls straight into the sea. If you have a shallow coast, you're stuck with old school factories. So is this the future? Or is this just a cool science experiment? Sound off in the comments below. This is one of those companies that I've been watching for a while. I've seen videos about them, and I'd love to go do an on-site. So if you'd like to see us go on-site and check this out for ourselves and do an on-site video, sound off in the comments, like and subscribe, all the things. And until next week, I'm Ricky with Vinci. Thank you so much for watching.